Look up at the night sky, and you might wonder when humanity will finally venture out into the deeper universe. But the sheer scale of the cosmos is almost perfectly designed to keep us exactly where we are. Take our closest galactic neighbor, the Andromeda Galaxy. It sits approximately 2.5 million light-years away from Earth. If we boarded a standard spacecraft traveling at 28,000 kilometers per hour, reaching those distant spiral arms would take 94.5 billion years. Even if we somehow built a ship that traveled at the speed of light, it would still take 2.5 million years just to make a one-way trip. Conventional thrust, firing a rocket engine to push a physical ship through empty space, is ineffective over these distances. Under current mechanics, humanity is permanently grounded inside the Milky Way. Einstein proposed a method to bypass distance entirely, a mathematical loophole in the structure of the universe. This theoretical shortcut was mapped out over a century ago by Albert Einstein. In 1915, he published a set of highly complex calculations known as the field equations. These 10 equations essentially form the master rulebook for how reality operates. This diagram shows the core mechanic of his theory. Massive objects, like planets and stars, act like a heavy weight resting on a mesh net. They physically bend and curve the invisible fabric of space-time around them. Because these equations are so mathematically dense, they don't have just one answer. Think of a quadratic equation from high school math, where solving for x can give you both a 2 and a 3. Einstein's math works the same way. It offers multiple, entirely distinct mathematical models for how space and time can behave under extreme conditions. Finding a way out of our solar system means taking these mathematical solutions off the chalkboard and looking for them in the real universe. The first of these exotic answers is solution A. In 1916, physicist Carl Schwarzschild solved Einstein's equations for a specific scenario, a mass becoming so infinitely dense that the fabric of space curves tightly enough to pinch off from the rest of the universe. For decades, this idea, the black hole, was entirely theoretical. It was a strange quirk in the numbers with zero physical evidence. Then, in 2019, scientists successfully photographed one. The dark void and its glowing ring of light looked exactly how the equations predicted it would. Humanity proved that a mathematical concept written on paper 100 years prior was physically real, which means we must pay attention to the other, even stranger answers hidden in that math. And that brings us to solution B. In 1935, Einstein and his colleague Nathan Rosen discovered another correct answer to the field equations, commonly known as a wormhole. This diagram shows the shortcut. Given a massive distance between points on a flat plane, the fastest route is bending space through a higher dimension so they touch, connected by a tunnel. In our three-dimensional reality, this tear manifests physically as a three-dimensional sphere. If you were to approach this spherical anomaly in a ship, the immense gravity would distort the light around you. You would see a curved reflection of the universe, wrapping entirely around the outer edge as you moved closer. Mathematically, this Einstein-Rosen Bridge provides the perfect tunnel to the Andromeda Galaxy. The problem is, ripping open the fabric of space requires a catastrophic amount of gravitational force just to generate the entrance. The only known object with that much concentrated gravity is a black hole. But black holes are a one-way trip. Anything that crosses the event horizon is crushed and permanently trapped. To make a wormhole survivable, you need an exit point. You need a mechanism on the other side of the tunnel that repels matter instead of pulling it in. This is solution C, the white hole. It operates as a strict boundary of no admission. Nothing can enter it, and trapped matter and light are violently expelled into deep space. The physicist Stephen Hawking theorized that as black holes slowly evaporate over time, all the consumed matter and data, which quantum physics states cannot simply be deleted, must be spat back out into the universe somewhere else. Physicists still fiercely debate whether a white hole can actually form. A system spontaneously lowering its entropy contradicts the laws of thermodynamics. Right now, our only potential observation is a mysterious gamma-ray burst recorded in 2006, which erupted brightly without any trace of a dying star. For a cosmic shortcut to be fully operational, both ends of the equation must hold up. The black hole engine has to pair perfectly with the white hole exhaust. Traveling through a gravity tunnel might seem like distant science fiction, but scientists are already testing these mechanics on Earth. In 2015, researchers in a Spanish laboratory successfully constructed a magnetic wormhole using a specialized copper oxide material submerged in liquid nitrogen. Every magnet has a north and south pole attached to each other. The researchers managed to physically separate a magnetic field, passing it into one side of their device and having it exit out another through an invisible gap. They proved the tunneling concept physically works for magnetic fields. By manipulating magnetic fields to mimic spatial tunneling, researchers proved that these theoretical shortcuts can be recreated in a controlled environment. It is the first step in moving these concepts from abstract equations into physical, lab-tested hardware. Even more solutions are waiting for our technology to scale up. Take the Alcubierre drive, proposed in 1994, which avoids a physical tunnel altogether. This animated diagram shows how a ship could theoretically travel faster than light by contracting the spacetime directly in front of landfall and expanding the space behind it, essentially surfing a ripple in reality itself. Intergalactic travel relies on the ability to manipulate the flexible fabric of spacetime. The blueprint for that manipulation is already written in the math. We are now waiting for the engineering to catch up.